Hey everyone! In this video, we're going to take our calculator a little bit further and figure out some of the cool things it can do to help us. So, in exercise 1 here, we have a survey that was taken of 10 low temperatures and high temperatures in Fahrenheit in the month of April to try to establish a relationship between days low and high temperatures. So first, we're going to construct a scatter plot of this bivariate data. Now, that's a very fancy way of just saying that there's two things we looked at. So bivariate, two variations of data. Now, we worked with the two-way tables last time, so we know when we're looking at two things at once, but we're going to construct this scatter plot just by plotting these points. Now, we're looking at the low temperatures being my x value and my high temperatures being the y value. So if I look here, 26 and 49 be about here. Then 28 and 50. 30 and 57. 32 and 54. 34 and 60. 35 and 58. 37 and 64. 38 and 66. 41 and 63. And 45 and 72. Okay, we can see just by looking at this data that it's not a perfect linear relationship, right? If it was perfectly linear, we'd be able to calculate the slope for every single point to have the same value. But the data is definitely in a linear pattern. So while it might not be perfect, I would feel good about calling this a linear piece. So what I'm going to try to do is figure out what my line of best fit is. So I want to try to draw a line that either hits the most of my dots or would cover the most of my dots or be closest to most of my dots. So I'm just going to sketch that in here. It would probably be something close to this. Again, definitely not perfect. Hint of the word best fit. It's hitting as much or getting as close to hitting as much as possible. But there's a way to figure out what this line is right from our calculator. And it's what we use linear regression for. So the same way we've been doing this whole past week, we're going to plug this data in. So I'll plug this into list 1, and I'll plug this into list 2. So just to remind ourselves how to get there, I go and I hit my stat button. I hit enter when I want the edit, and I've already put my data in. So if you need to pause the video real quick and enter all your data, there should be 10 values in each list. But I plugged in list 1 as the x values and list 2 as the y values. Once I have a moment to have all my data in, I'm going to go ahead and hit stat. I hit the right arrow to calculate. Now, we've been using one variable stats this whole time. And we also have this 2 variable stat, but we're not using that. We're trying to figure out the line of best fit, the line that's going to hit most of my data. So if I go down a little bit past it to linear regression, ax plus b, well, that looks like the line we've been using all year, right? Y equals mx plus b. So I'm going to use that linear regression and hit enter. Notice my x list is list 1, like we said. My y list is list 2, like we said. And I'm going to just hit enter all the way down to calculate. And it even gives me like y equals ax plus b at the start there. So we know linear. And if you wrote mx plus b, that's fine. I'm just going with what the calculator gave us. A, it's giving me the value to be like 1.1626. And it gives us a value for B as 19.0736. So I'm going to just put this all together. Now, it didn't give me a place to round to, so I'm going to just round to the nearest hundredth for this one. But our line should look like y equals 1.16x, because I'm plugging the a value in as the slope, plus 19.07 as the b, the y-intercept. So it's not perfect, right? We kind of know that it's not going to be. But this line is going to get as much of those dots on the line, or as many dots as close to the line as possible. So that's what we call our line of best fit. And we do it again by linear regression. So now if I use that line of best fit to estimate the high temperature for a day, that gives us the low temperature of 42. Remember, when we're thinking about that, the low temperature is my x value. The high temperature is my y. So I'm just thinking about this equation, y equals 1.16x plus 19.07. If we plug in 42, we want to know what we would get out. So again, I'm plugging that right into the calculator. $67.79. And usually we talk about degrees to the nearest degree. So 68 degrees Fahrenheit. Okay, so if I break this all up, though, explain what the y-intercept of this model represents in the context of being modeled in this problem. So based off this problem alone, the y-intercept we know is when x is equal to 0. It's our initial value. So when the low temperature is 0 degrees Fahrenheit, the high temperature for the same day is about 19 degrees Fahrenheit. Okay, so basically when one of our values is 0, the high starts at 19. Now if we want to interpret the slope, let's say for every additional degree is increased. Low degree is increased. The high degree temp will increase by 1.16. I think we said it was. Yep. So I can add my degrees Fahrenheit to that too. But so basically, for every additional low degree, so as the x value increases by 1, my y is going to increase by another 1.16. And then finally, would you categorize this relationship between low and high temperatures a positive correlation or a negative correlation? Well, I would definitely call it a positive correlation. So as one's increasing, the other's increasing. So that's positive, just like my slope would be positive in this case. Again, as one increases, the other increases. That is a positive correlation there. Okay, cool. Okay, I want you to pause the video here and attempt this one. So in this case, you don't actually have to plug any data in. So you don't have to plug any data in this case. So just take a moment and think about the two things that are here in this question. I want you to think about it logically for a second. So go ahead and pause. Okay, so let's think about this. Are the data positively or negatively correlated? Well, we should have seen that they are positively correlated, right? As one was increasing, the other was increasing for the most part. Like even between 8 and 9, maybe a little bit of a decrease by the Y value, but nothing too significant. Like I said, we're just thinking about the majority of these. It's not going to be perfect. But for B, this is a really important question. Now, this is one that I want to stick fresh in your mind as we're thinking about it. Does the number of firefighters cause the damage done to the house? Well, that should definitely be no, right? We're calling on these firefighters to help us. We can't put the blame on them for it being more damage, right? There's just a bunch of things that could have happened, right? So there's outlying factors that could have happened, like in the thought of maybe the fire was more severe, so there was more firefighters there. Sometimes even maybe the fire is closer located to the house, right? So maybe there's going to be more there. But the big thing about this is just because two variables have a strong correlation does not necessarily mean that it's the cause. So correlation in this, we can never tell what the actual cause is. So correlation and causation, no good together. And that's going to talk about a little bit more tomorrow in class. But for exercise 3, generally the fuel efficiency of a car changes the weight of a car. A survey of some cars with their weights and gas mileages is shown below. Let's plug these in. Now, when I plug this in, we're going to just plug the data in just as it's given to us, but there's something that we got to keep in mind. My X value is in thousands of pounds. So you can either plug it in the thousands or you could plug it in regularly, just as long as the end we think about that. So find the equation for the line of best fit using your calculator, round both coefficients to the nearest tenth. So take a second and plug all of those in. So let's just plug those in. Remember, going to stat edit into list 1 and list 2. So I have my data in here. Remember, I went to stat edit, entered the data in. We're going to go to stat calculate. Remember, our new thing here is going down to linear regression. List 1 and list 2 are in there for us. And I get my equation of my line to be y equals negative 8.09 735 x plus 68.1 or 68.0935. Now again, we've got to be careful because this is in thousands of pounds. So just keep that in mind as we go to plug in. Let's just take a peek at what would happen if we put these values into thousands first off. So let's see if anything changes about this. So in my calculator, the same two lists, but now instead of 3.7, I have 3,700 and so on. So basically I times each number by 1,000 since it represents thousands of pounds. So in here, if I go to stat calculate, and I'm going to hit 4. Now, the y value is still the same, my y-intercept at least, but notice my decimal place moved a little bit here. So it might be better for us here to think about these data in this thousands of pounds realm, just so we have that. So I'm going to actually round not to the nearest tenth in this case. I'm going to leave it a little bit longer. But negative 0. Let's say 0.081 x plus 68.09. Notice the y-intercept's still the same because I didn't change anything about my y values. And the weight changes because it's y over x. So that's why it's getting smaller, because those are thousands of values now. So we just want to be careful of something like that sneaking up. But something cool our calculator can do for us also, I can graph these points right on the calculator and make my picture here. So if I go to second stat plot, so the y equals has stat plot written above it. So that's why I hit second stat plot. I could hit enter. I could turn stat plot on. And then I can go to zoom. And once I hit zoom, I see down at the bottom, zoom 9 is zoom stat. Now we can see what our residuals would look like. So we see where all these regression points are. And I can just do a rough, because this is just asking me for a rough sketch. So something along that. And all I need from that is to recognize that now we are dealing with a negative correlation. Okay, and it says because as one increases, the other's decreasing. That's how we know we have a negative. So which parameter would we look at to tell the correlation? Always the slope. If the slope is negative, it's going to be a negative correlation. And if it's positive, it's going to be a positive correlation. Now, if a car had a weight of 4,300 pounds, what would this model predict as its fuel efficiency? Round to the nearest integer. So it's in pounds. So that's why I'm using the formula converted into pounds here. So all we're going to do is y is equal to the weight. I'm sorry. Y is equal to x is my weight. So 0.0081 4,300 I'm going to plug that right in. So second quit, negative 0.0081 4,300 plus 68.0935 33.2635. And we round that to the nearest integer. It's saying 33 miles per gallon. So that would be my best fuel efficiency there, which makes sense because it's a heavier car. If we wanted to purchase a car that got 40 gallons to the mile, 40 miles to the gallon, what would the weight of the car be? It's the nearest 100 pounds. So this time we'd be plugging in to y, because we just think about which part of the equation this is. So I'm going to subtract the y-intercept from both sides first. I'm going to let the calculator do the work for us there. 40 subtract 68.0935. Oops. So when I solve that to the nearest 100 pounds, 3,500 pounds. Okay. One last idea that we need to cover here is that there's other types of regressions as well. So we know that there's linear, as we just saw, those relationships were linear, but exponential and quadratic graphs make their way back for us here. So if we're looking at this in exercise 4, excuse me, we should be able to tell that each scatter plot has a different type of regression that would be best to find the equation that best fits their data. So I would say for the first one, we'd be looking at exponential. Second one, we'd be looking at a quadratic. Third one, exponential again. We could see that kind of curve flattening out as we look at it. Then D looks more like a line to me, so that looks linear. I would say linear again for E, and then quadratic. Smiley or frowny faces, remember, are quadratics. Anything that starts low and ends rapidly up. And then a line. So we could have those as well. So to finish up those ideas, in this case, we have biologists are meeting the number of flu cases as it spreads about a particular city. The total number of cases, Y, was recorded each day, X, after the total reached 16. The data of the first week is shown in the table. Use your calculator to find the exponential regression. So we're told, so you're not going to have to guess here. It's telling us to use this equation and to round all my parameters to the nearest hundredth. So we're going to clear out what we got. Stat edit. I'm clearing out my list. So remember, I hit the up arrow, clear on that highlighted part, and click it down. So what I got? 0, 1, 3, 4, 6, 7. So 0, 1, 3, 4, 6, 7 are the data values I put in for the X. So I'm just hitting enter each time or down each time. I got 16, 18, 22. Oops. 25, 33, 35. Stat calculate. This time, I'm skipping by linear regression. I see quadratic would be 5 if I was dealing with something like that. But exponential, if I keep going down, I see X reg, and I hit my enter all the way through. It tells me my Y and my B value. It said to round to the nearest hundredth. So I'm going to say 15.92. Times B, 1.12. Raised to the X. So we make it look like that Y equals A times B to the X. This is an exponential equation, and we're good. Based on this equation that we got in part A, how many total cases of the flu were there be after 2 weeks? So 2 weeks, remember, if I look, this is in days, not weeks. So I'm not plugging in 2. I'm plugging in 14 days. So y equals 15.92 times 1.12, plugging in a 14 up at the top. 15.92, 1.12 raised to the 14, 77.80. Okay, so we're thinking about 78 cases. Which makes sense. It's growing exponentially. It's going to grow faster and faster. According to your model, by what percent are the flu cases increasing on a daily basis? Remember, percent's got to be between 0 and 100. I get that from looking at this, right? We did that a while back with exponentials. So I can't have 1.12 there, but if it's bigger than 1, it's increasing. So I'm subtracting out that 1. So 0.12, and we convert it to a percent. So we either times it by 100, we move it 2 decimal places, but 12% is what it's increasing by on a daily basis. Now, hospital officials will declare an emergency when the total number of cases exceeds 200. On what day will they need to declare this emergency? So, needs to exceed 200, so we need to think about that too. But I think it's just probably better to guess and check on this one. So we already knew it was at 68 at 14. So we could just guess and check here. Let's see what I get. I'm going to steal this and just pull it right down. Let's say what happens at 20 days. Not yet. So again, I'm just going to go up and steal that back down. Let's see, maybe 30. Well, 30 was way too big, right? So that'd be more than 20. Let's say 24. Okay, getting closer. 23. See what 22 looks like, because we just want it to be exceeding at first. Okay, so at 23 days is when we would run into an issue. So I just guessed and check on that one for when it was bigger than 200. Okay, last question of the day. The cost per widget produced by a factory generally drops as more are produced, but then it starts to rise again due to overtime costs and wear of the equipment. Quality control engineers record the data at cost per widget compared to the number of widgets produced. Their data is shown below. Why should a quadratic linear model be considered for this data as opposed to linear and exponential? Well, think about what they said in here. Genuinely drops as more products, but then starts to rise again. Okay, so it's like one that's going low and then high, that's always quadratic. Okay, so I could look at the data and we could verify this. And I'm going to show you again how to use our scatter plot. So let's clear out our data. I hit the up arrow, hit clear, then down. Up arrow, clear, then down. 33, 88, 110. 135, 154, 190. Oh, wait, I changed that one to 154. Sorry about that. So that's 154, not 155. Then we get 9.32, 2.63, 1.42, 1.32, 2.12, and 5.50. So we're going to go to y equals, but remember we're going to do second y equals. My stat plot's already on. We're going to go to zoom, 9, and we can see our quadratic drawn in there. So you don't really normally need to be able to plot your scatter plot on there. It's just pretty cool that the calculator does it for you. Okay. All right, guys, that's it. I know we did a lot of calculator work on here, so it's a little longer video than usual. But thanks so much for watching. Hopefully it helps make sense of how to use the calculator a little bit more.